Good morning. My name is Leong, number EB20023. I am from section 01A.
So hi, my name is Sheng and my student ID is EB20183. So now I'm going to start the presentation. So for part A, diode testing and threshold voltage, we need to determine the threshold voltage of the 1N4001 diode using the diode checking capability of a digital display meter. So refer to the electronic device and circuit theory. First, we put a 2 milliampere current into a diode, and this is in a closed loop circuit. So we simulate this in a multi-sim live. Measure the voltage here, and we get 0.673 volt. So the answer, the threshold voltage Vt is equal to 0.637 volt. So next, for part B, we need a diode bridge with transformer and its input. So this is our circuit diagram, and this is the waveform. So the voltage start from 0 and go through the V peak, which is 16.940, and then it go through 0, this is a positive cycle, and next he start the negative cycle from 0 to the V peak, which is negative 16.940, and go through 0 again, and here is the negative cycle. So next about the diode. So first, the current in a positive cycle, the current here flow to diode D1, and next flow to the resistor, and then flow through the diode D4 and flow back to the transformer. And next, for the negative cycle, the current flow to the diode D2, then flow to the resistor, and last flow to the diode D3 and back to the transformer. So the current always flow to the positive. 这个怎样讲啊？
The voltage always positive.
The Vout is always positive because of the diode. Here is the waveform. So the diode start from 0, then go to the maximum 15.488, and then slow down. The curve is not smooth here is because the threshold voltage of the diode. So he moved to the V peak again, and then go down again. So for the calculation part, V peak is equal to square root 2 multiplied by V RMS. So square root 2 multiplied by 240, and this is the answer, 339.41 volt. So to calculate the transformer output, so V in is equal to the V peak, and here is the ratio of the transformer 1/20, and so the V input is equal to 16.971 volt, and the V out is equal to the V in minus 2 times Vk, which Vk is the threshold voltage of the diode, and here is the answer, 15.625 volt. So the VDC equal to 0.6 in a full so 0.636 V out which is 9.9375.
And then for part C, output filtering. In this experiment, we are to add a capacitor of 100 microfarad to parallel to the 1 kilo ohm resistor. So this is the constructed circuit and the waveform for input and output voltage. So from this output voltage graph, we can see that the peak in this positive voltage is 16.929 volts, and for the negative peak is negative 16.929 volts as well. But for the output voltage, the peak is 15.441, while the curve itself does not drop below here, so the voltage is relatively constant, unlike the input voltage, which is rising from 0, rise to top, go back to 0, go back to negative, because the capacitor here, when the positive cycle of the AC source, after rectifying, the voltage will always be positive, and then during the first cycle, the positive cycle, there's voltage across the capacitor, so that it acts as a open circuit and then is charging. After the peak, when the input voltage drops, there is less voltage to the capacitor, so that now the capacitor acts as a voltage source and discharges to the resistor, so that the resistor, even though the input voltage drops to 0, the capacitor supplies voltage across the resistor, causing the voltage constant here. Next, to find the VDC. To find VDC, we will directly use the formula. For the VP rect, we will use the V out from the diode bridge. So 15.625 act as VP rect, which is peak voltage after rectification, and we get 14.0625. The main reason the input voltage is different than the output voltage is because the capacitor acts as an source when the input voltage drops to 0 to begin negative cycle. When there is no voltage across the capacitor, it will act as a source, and then it discharges its voltage across R1, so that the voltage across R1 will become constant without dropping to 0. And when the voltage rises to a point where the capacitor discharges, the output voltage rises again, and then the capacity starts to charge again. And then after the peak voltage ends, it starts to drop, and then the capacitor starts to discharge again.
So next is about the discussion. So for part A, from the multi-sim live online simulator, the diode has a threshold voltage of 0.637 when a 2 milliampere current is passed through. Based on the method used in the textbook, electronic device and circuit theory, which is different from usual 0.7 voltage used in calculation involving a silicon-based diode. So next for part B, from calculation, the Vin determined is 16.971 volt and Vout is 15.625 volt. While the simulation shows lower reading but still negligible difference, where Vin is 16.940 volt and Vout is 15.488 volt. Among the possible reasons is the resistor in real connection wire, which is usually neglected in calculation. The curve of Vin and Vout also different, where Vout is not smooth increase from 0. This is because the activation voltage needed for diodes to pass through before they can overcome and pass current through.
So in conclusion, from this lab, we know that the diodes allow current to flow in one direction only. This is important to convert or rectify an AC current to DC current for various components, electrical components. Also, in part A, we know that when diode allows current to pass through, it introduces a threshold voltage that needs to be overcome before current can pass through, which measured in this lab is around 0.673 volts. The main function of a capacitor in a diode bridge is to ensure constant voltage even if the input voltage drops, as seen in part C. And then the voltages calculated is always different than in simulation or in real circuit. The main reason for this is supposed to be the resistance in the power source, wires, and loss of energy to heat. That is all for our lab 1. Thank you.